Okay, welcome back everybody to another edition of Awkward Learning, Distance Learning with Mr. Morales. Today we are going to be doing corrections on the Big Bang and Waves test, one that a lot of students found difficult. So let's dive in and see how we can better understand this material. All right, first question, asking us about the Big Bang Theory. So it's giving us several possibilities and asking us which one applies to the Big Bang Theory. First off, it suggests that maybe the Big Bang Theory states that the universe is constantly getting warmer. Well, remember, in the beginning, the universe was hot. It was so hot that atoms couldn't even stay together. It was just particle soup. So, no, it couldn't get any hotter than it was in the beginning. In fact, it's doing the opposite. It is cooling down. So, that's nonsense. Let's look at the second one. The universe is approximately 3.8 million years old. That sounds like a big number, but 3.8 million is tiny. No. Life on Earth is older than that. So certainly the universe is quite a bit older. 3.8 billion years? Nope, still not there. 13.8 billion with a B is more like it. So, nope, we don't like option 2. That is not close. The universe has grown extremely fast from a tiny point. Yes, we like the sound of that. That's what the Big Bang suggests, is that all time and space has originated at one point, expanded unbelievably quickly from that one point. So C. And obviously we can rule out D since the first two were nonsense. Okay, number 2, cosmic microwave background radiation. Students really struggled with this idea. I can tell you that what most students seem to think was that it makes up most of the light we see. No. It's in the name. It is microwave background radiation. So just knowing that it is microwave waves should tell you we can't see it. If we think about the electromagnetic spectrum, microwaves make up one part, and visible light that we see makes up a tiny fraction of all radiation. We can't see microwaves. So the story with cosmic microwave background radiation is that it is the light that first escaped that soup of the Big Bang as the universe very first was formed and started to cool. So in an expanding universe, that light that escaped is stretched out. Its wavelength is longer, and now when it reaches us, it has gone from light to microwave. That microwave radiation surrounds us. It is all around us. So let's look at some of our options here. From the formation of the Milky Way galaxy. Remember, the galaxy is just where we are, and that happened long after the universe was formed. If this said universe, we'd consider it, but nope. Not Milky Way, is emitted by a type 1a supernova. No, that's a nonsense answer made to sound very sciencey. Hits the Earth from every direction. Yes. So you remember the story that there were some scientists who set up a giant antenna trying to learn things about, they were trying to aim their giant antenna out into space and see what they could find. And what they found was this sort of background static, no matter where they pointed it. And that was the cosmic microwave background radiation. And so they stumbled upon this great discovery once they figured it out, of the origin of the universe. So yes, it hits Earth from every direction. Okay, number 3, the expansion of the universe has occurred at a uniform rate, began very quickly and then slowed down, will eventually slow and stop, or did it just end at the Big Bang? Well, scientists debate this to this day, but the consensus is that it happened very quickly in the beginning. Massive exponential growth, and then it has slowed down, but it's not going to stop. So there is some thought that maybe it'll slow and stop and the whole universe could start contracting again. But most scientists tend to agree, no, that's not likely to happen. Instead, it's probably just going to eventually pull apart and the whole universe will just kind of come undone. All right, let's look at number 4. In physics, a wave is, oh my goodness, I must have been feeling silly. I just gave you a bunch of nonsense and then one logical thing. Is it when people stand and sit in a cool pattern at a stadium? Well, that is a wave, but definitely not a physics wave. What you do when you see a friend across the street, not in physics. The thing surfers ride, totally gnarly, but again, not a physics wave. A traveling disturbance that carries energy from one place to another. Absolutely. All right. Number 5, the medium for sound waves. Well, we have to know what a medium is. So a medium is the place where waves travel. So what the medium is going to depend on what kind of wave we're talking about. We're talking about sound waves, and the sound waves that we hear are generally traveling through the air to our ear. So A is nonsense, as is C, and as is D, because if you know that what the definition of a medium is, then you know that you are looking for a place. And in this case, the only one that makes any sense would be air. Okay, as frequency increases, what happens to wavelength distance? Well, if we go back and kind of look at our equations for frequency and wavelength, we know that frequency equals velocity over wavelength. So what we see here is an inverse proportion between frequency and wavelength. When one thing goes up, the other one goes down. We definitely saw this when we were talking about the Doppler effect, that as the wavelength got smaller, when something was moving toward you, then the frequency would go up. So wavelength decreased, frequency increased, meaning frequency being the pitch if we're talking about a sound wave. And the opposite is also true. As frequency will go down, so think a sound would be deeper as the wavelength increases. Again, thinking about the Doppler effect, when we saw the video of the trombonist coming down the hill, as they came closer, that wavelength was getting shorter and shorter, and the frequency was very high. As they got further away, the wavelengths were more spread out, bigger, and the frequency went down. So as frequency increases, wavelength decreases. So that's an inverse proportion. We got one thing in the numerator on this side of the equal sign, one thing in the denominator on that side of the equal sign. Okay, in a transverse wave, a transverse wave, the medium moves what relative to the direction of wave propagation? Well, a transverse wave is a wave that moves like this. So the direction of travel is this way, but things are moving this way. So we say that something that is moving in the 90 degrees to the direction of travel would be perpendicular. And that's different than like a longitudinal wave. So a longitudinal wave, we could diagram saying that everything is moving in the same way. In which case, if this was, so this is transverse. If I was asking about a longitudinal wave, we would say that it was parallel because everything is moving in the same plane. All right, stay tuned for some CRET work next.